All right. How many of you just went back to the 80s when you heard that track? How many of you thought of a specific film? Yeah, there we go. So I'm going to start off today with talking about a few films that I love because they really influenced me when I was younger and recently as well, that are all about time. And first of all, I'm going to get you to guess some of them, okay? Don't worry, the whole talk is not about films, it's just the first 30 seconds. So, first of all, what film is this? Star Trek 4, right? So if you need an extra clue, there you go, right? They travelled back in time, really cool. What about this one? The Time Machine, the original. Now this guy, I got to tell you, I loved my equipment when I was a scientist, but not as much as this guy. He really, you can see the way he's holding it. He really loves his equipment. If you don't believe me, let's just have another look. You guys okay? Whew. It's pretty hot and heavy. In the same film, they gave us an image of what men would look like 800,000 years in the future. I think we're fucking getting there. We're close, right? I think we're doing pretty well. But I was on the university campus for many years, so maybe I'm a bit skewed. What about this one? All right. The thing I love about this image is it gives away a little clue that most people didn't notice. Doc Brown came up with the idea of the flux capacitor when he was hanging a clock above his toilet. He pissed on the seat, people. Do you realise that? The porcelain was wet. That's why he fell. That's why the whole film happened, because he pissed on the seat. Yeah, it's a little detail that most people miss. Anyway, what about this one? Interstellar. Interesting because this one really talks about how time changes around large gravitational objects, and we'll come back to that a little bit later. What about this one? The Arrival. Literally one of the best sort of time and communication films ever made. Extraordinary. One of my favourite personal films, and one that draws together two things I love: communication of science and time. All right. So, we have been interested in measuring time forever, all right? We started off, some of the very first clocks were actually water clocks. Now you can imagine they were pretty accurate, right? Dripping water clocks. And they were found in some of the ancient Egyptian tombs. This was in one of the tombs around the time of Tutankhamun's grandfather, if you can believe that. Then we moved on to sundials, which you're probably all familiar with. Some of us even had them in our backyards. You can buy them at Bunnings. But they were making them back in the days of the ancient Egyptians as well. They were pretty inaccurate, but they used the sun to tell time. I'm going to give you all a moment so you can... Are you hearing it? Some people are hearing it? Sorry. But timing with sand was really interesting because it meant you could move these things around and they weren't so fixed to the ground, which was really a great way of timing things. Of course, again, inaccurate, depends on humidity, a whole lot of other things. So not a great way to measure time. Now, Christian Huygens, who's an amazing scientist back in the late 1600s, he came up with the design for the pendulum clock. He didn't actually build it himself, but he invented it. And this was one of the most incredible clocks for about the next 300 years. And, it's still used today. You can still go and buy them. They're incredibly accurate because they have something that oscillates in a nice specific pattern that depends on the length of the pendulum. And you can calculate that really cleanly. Before I lost my hair, it looked exactly like that, by the way. Yeah. Okay, so now we're going to switch across to one of the reasons why I think time is so important. To do that, I have to talk to you a bit about navigation. There's some maths in here, so if you want to leave, you can leave now. All right, we navigate by using two numbers. The first one is latitude, the second one is... Right, okay, latitude is really easy. You just take a measure from the equator towards one of the poles. If you're at the pole, it's 90 degrees. If you're at the equator, it's 0. It's really easy to work out your latitude because you just have to look at how high the sun is in the sky or know the length of day. These are easy things to figure out. Longitude is a measure around the globe, and we start that measurement in Greenwich at 0 degrees. And of course, there are how many degrees in a circle? Right, so 360 degrees of longitude around the globe. And we pull them into nice little increments, and I'm going to talk to you about how they work. Okay, so here's the maths bit. All right, there's 360 degrees of longitude around the Earth, starting at Greenwich. Each day the Earth rotates once, and there are 24 hours in the day, each of 60 minutes. So how many minutes are there in the day? That's okay, I'll work it out for you. There's 1,440 minutes, and that means that if you divide that number by 360 degrees, each degree of rotation of the Earth happens in 4 minutes, okay? So think about this. That means 15 degrees around the Earth is equivalent to an hour. Let me give you a really simple example of this. The distance between Perth and Melbourne is pretty much exactly 30 degrees of longitude. How many hours behind us is Perth? 2 hours, right. No. You're also thinking of Queensland. But yes. So this is interesting. If I know that it is 12 o'clock in Perth, I know it's 2 o'clock if I go 30 degrees away from Perth, right? So I can work out my longitude if I can take a clock with me. So if I'm over in Perth, we'll say this is, how long is this cable? I'm over in Perth, and I look up and the sun's in the middle of the sky, and I make a note of the time, and then I start traveling to the east. If the sun gets to its apex at a certain time, and then I pull my Perth clock out and realize it's 1 hour ahead of that time when it should be, I know I'm 15 degrees away, right? So I look up in, somewhere halfway between Perth and Melbourne, and I say, okay, it is noon because the sun's in the middle of the sky. I pull out my Perth clock, and it says 11 o'clock, not 12. I know that I've traveled 1 hour around the globe in terms of longitude, which is equivalent to 15 degrees. And I can work out exactly how far I've gone. Now, there's a catch there. I need to know what time it is in Perth, which means I need to be able to take a clock with me. The water clock, sundials, pendulum clock on the back of a flatbed truck, I don't think so. I need something I can carry, right? Now, to go a step further, imagine trying to do that 300 or 400 years ago on a ship. Incredibly difficult. Okay, and in fact, a really big disaster occurred back then where 4 naval vessels didn't quite have their longitude calculations correct because they didn't have that clock to carry with them. And so somewhere between 1,400 and 2,000 people died as a result of these 4 ships crashing into rocks because they missed the pathway back into the English Channel. And as a result of that, the UK Parliament at the time set up what was called the Longitude Act. This was essentially a prize they set up for people to win if they could work out how to determine longitude at sea. And there were a whole lot of these commissioners of longitude, believe it or not, they were all men. And one of them was this guy you may have heard of, Sir Isaac Newton. Now, he thought the answer to this problem was in the stars, the planets. The idea of it being a clock that you could carry from one place to another, he said, wasn't possible. So at this point, I think the world needed a miracle. They needed a carpenter. His first name started with J. What was his name? It was John. Right? John Harrison. Now, this guy was a carpenter, and just before the prize was offered, about a year before, he started making clocks. He wasn't trained, he wasn't an engineer or a scientist. He was just starting to make clocks when it was announced. This was his first clock called H1. He submitted it for the prize, but it didn't keep time accurately enough, and he didn't win it. Now, the prize was quite substantial. In today's dollars, it's millions. He then made H2. The first one took him 5 years. The second one took him 2 years and 3 years of testing. It wasn't accurate enough, so he ditched it. And he went on to H3. I mean, he was really good at naming these things, by the way. H3 had a flaw, took 17 years to get to H3, but it had a flaw relating to some springs that were in it where we didn't have the science understanding necessary to make it work for another 200 years. So he was kind of behind the 8 ball. Then he created a masterpiece, right? This is H4. It looks like the sort of pocket watch that you might have. It's actually the sort of one you'd see in Alice in Wonderland. If you look at the scale there, it's really quite big. had some amazing features. For every second, it actually ticked 4 times, and you could wind it while it was running. Now, when he tested this over a period of 9 days, it only lost 24 seconds. He still didn't win the longitude prize. They screwed him. He then went on, he was getting pretty old at this stage, by the way, and he made H5, and King George at this point got involved, and he tested it himself. And he found that over a longer period of testing, it only lost 1/3 of a second a day. And he actually pushed Parliament, not the Commissioners of Longitude, to give him at least some of the prize to compensate. He actually got quite a bit of money over the period of his life, but he never actually won the longitude prize. But when you took his clocks onto a boat, they kept perfect time, which it didn't matter what was happening in terms of the roughness of the sea or whether you could see the sky or not, and he was able to solve the longitude problem. So time became this crucial element of navigation. And this guy, John Harrison, who most people have not even heard of, actually solved that as a carpenter making clocks. Okay, so a bit of a hero. So we've come a long way since then. And of course, you've probably remembered those watches that had all those great labels long ago, quartz on them. Well, quartz has this really cool feature. If you put an electromagnetic field across it, it makes it oscillate. And to make a good clock, you need something that oscillates, because that's how you work out time and seconds. And so we started using quartz in all our watches and so forth, and we could suddenly make these super accurate watches. Here's a picture of a watch that I owned quite some time ago. I've still got it. I took it down to one of those little jewelers in the shopping centres one day, and I said, it's not ticking, it's not working, I need you to change the battery. And this guy looked at me, and I was an optical physicist at the time, and he said, dude, you got to get out more. And I looked at the fucker. I've never been back to that jeweler guy. Bit of shame. There's clocks in the sky as well. You've probably all heard of Jocelyn Bell Burnell. She was the one who discovered the pulsar, and her a-hole supervisor got the Nobel Prize for it. And that has never been rectified. I've interviewed her twice on my radio show. She's an amazing person. But these clocks can run up to 700, the fastest one is 716 beats per second. These are rotating stars of a particular type that sweep out like a searchlight into the sky, and we pick these up. So there are clocks in the sky. The ones that I find amazing, though, are the atomic clocks, and this is what all of our timing now is based on. So on the left, you can see a cesium clock. This is the sort of clock that the world's time is based on. There's one in Boulder, Colorado. In the good old days, I'd be able to bring an old radio in here and tune into it on shortwave radio, and actually you'd hear it beep. You can't do that anymore. It's all online. But cesium clocks are the standard. The strontium clock on the right I find is fascinating. It's a far more sophisticated and more difficult to build clock, but it will lose 1 second in the next 15 billion years. That means if you started this sucker when the universe started, it'd still be good. Won't have lost a second yet. A couple of billion years before it loses one. So we can make these incredible clocks now with incredible precision. Of course, the second you start making clocks with this level of precision, it means that you start to learn more and more about the universe. Okay, so enter this guy, who you may have seen before, Albert Einstein. He really fucked things up for everyone, didn't he? Newton was doing well. He was wrong about the clock thing on the boats, and then this guy came in and really gave it to him. But one of the things that he taught us was that when objects move incredibly fast, they experience the effect of time dilation. So all of a sudden, time that we thought was the same everywhere, Einstein said, no, that's not the case. And so he came up with 2 very, very prominent theories you would have heard of, special and general relativity. I'm going to have a quick talk about those. Okay. So in special relativity, we're talking about things that are just moving very, very fast out in space. And I want to give you an example. If I was to send you all on the rocket ship away from Earth, we could work out very easily, actually, how much time you would experience compared to how much time I would experience here on Earth. So let's have a look at some of those calculations. Say 100 years passed for me, and you were travelling at half the speed of light. The time dilation effect you would feel would be 87%. So you would only feel 87% of the time that I feel, which would mean only 87 years would pass for you on the spacecraft. So if we met up again, you would be younger. Now that's not very fast. Let's notch it up to 90% of the speed of light. At that point, you're experiencing this 44% dilation, and for you, only 44 years will have passed by. 99% of the speed of light, all of a sudden, you're only experiencing 14 years compared to my 100 years on Earth. Now, when we think about this stuff, it messes with our brains, but it is real. It is real. So, the second one that Einstein talked about was general relativity. And you may remember this if you've seen the film Interstellar. This is where when you're close to a very large gravitational object, like a planet or a star, or in this case a black hole, time travels slower near those large objects. Again, messes with your brain. Is it real? Now, we've done many experiments over the last 4 or 5 decades to demonstrate just how real this is. But how does this affect you? Well, it actually affects you every day. And let me give you an example of why. We all rely on the GPS network, right? I mean, did you have trouble getting here? How many people in this room knew where this place was but put it into their GPS in the car anyway? Yeah, we do it, right? We want to know exactly how long it's going to take to get here, right? So what we forget is the GPS network gives us 2 things. It gives us our exact location. It also gives us our exact time. And both of those are necessary. The GPS network is made up of usually in excess of 24 satellites that are moving around the Earth at quite high speed. And by that I mean 3,000 meters a second. They're in orbit, but they're not stationary as we might imagine them to be above us. They're actually moving around very, very rapidly. They're also near the Earth. Now, if we think about Einstein, he said that objects that are really close to the Earth must experience time slower than objects further away, which means the satellites shouldn't experience time in the same way we do standing on Earth. Similarly, they're also moving very, very fast, which means according to special relativity, they should experience less time than we do. So being further from the Earth, general relativity, they actually experience 45 microseconds, they see that faster than we do. So their clocks run faster than ours, okay? Because of special relativity, they're moving very, very fast. Their clocks run slower. These 2 things kind of cancel each other out in a bit. And if those of you who are really good at maths will worked out the difference between these 2 is 38 microseconds. 38 microseconds, who cares? The GPS system that we use has an accuracy in the nanosecond range. So 38 microseconds is 38,000 nanoseconds. So these errors are really significant. And if we don't correct for them, they will actually stop the GPS system from working effectively for us. So we absolutely have to make sure we do something to fix this problem. So when engineers designed these satellites and the little atomic clocks that sit on them to determine time, they actually designed them to run 38 microseconds slower than they need to compensate for that effect of special and general relativity. If we didn't do that, the whole system would fail within a few days. So special and general relativity are used by pretty much everyone in the room, I suspect, every single day. You may just not be aware of it. Okay. So let me give you another quick example here. If things age slower near the center of a gravitational or close to a gravitational object, then what does that mean for the center of the Earth versus the Earth's crust? Wouldn't it sort of make sense that the center or the core of the Earth was younger than the Earth's crust? I mean, forget all the geology stuff of things moving around. Wouldn't you expect that to be the case? Well, in fact, Richard Feynman, very famous physicist, back in the 60s, he said that is the case. You've got to take relativity into account, general relativity into account, And he did a calculation. He said it's 2.5 days. 2.5 days younger. Now, just a couple of years back in 2016, a new paper came out and said, Richard Feynman, just like Newton, wrong. Wrong. It's actually 2.5 years. Now, remember the Earth is over 4 billion years old, but over that period, the effect of general relativity, if there was no geology moving things around, would mean that the core of the Earth was 2.5 years younger than the crust of the Earth just because of that effect of time dilation. Okay? So as we get better and better at measuring time and we understand more and more about time, we actually are learning more and more about the universe and how it's structured. And that's one of the things that, for me, makes time so fascinating, because you don't really think of time as a tool for exploration, but it absolutely is. And these days we have exquisite ability to measure time. And I hope that tonight I've given you an idea of just how important time is, not just to our day-to-day lives, but to the way we explore the world and we explore the universe. So on that note, I will say thank you for your time.
Not bad for some guy with a cool blazer, right? All right, if I can get some house lights. We have a little bit of time for a few questions for Shane. Yep, just at the front here.
How does strontium clock work?
So the way all these clocks work is they take an individual atom, if you will, and think of an atom being able to have an excited or a non-excited state. So you can change the energy sort of contained within that atom. To excite it, you have to give it a certain amount of energy. And you do that by using particular wavelengths of light. Now, light has a frequency. So by giving the atom a very specific frequency, or a number of oscillations, if you will, and remember, oscillations are what allow a clock to work, you can fine-tune that to exactly what it is for that particular atom. The cesium is used for a specific reason, because it has that beautiful, clean, excitable state. And so that's been the atom of choice. The strontium clock won't be in widespread use, I don't think, but cesium is a relatively easy one to excite with a particular frequency of light. And it's that oscillation of frequency that allows a clock to work just like it does in a pendulum clock or a quartz watch, all the same.
All right, any other questions? Yeah, just at the back there.
So Shane, those movies that you start there, any of those sort of really irk you about science? You go, oh, that's not right.
What movies irk you about science?
Yeah, look, I think one of the things I learned very early on in my career is that if you wanted to get any enjoyment out of films, you kind of had to let some shit go, you know? and like, you know, one of my all-time favorite films, was what got me into science. So The Time Machine and the book by H.G. Wells was one of the things that got me into science. So you can imagine, I was learning, and then I got to a certain point, probably late high school, early university, and I thought, oh, fuck. This is bullshit. But I still love the film. So there's some films that I think are a lot better than others. Interstellar, for me, is an extraordinary example of demonstrating time dilation. Now, there's some parts of that film that I'm not big on, but the majority of it and the way it conveys even the intensity of emotion of this few individuals getting very close to a black hole and their time slowing down so significantly that the main character's daughter back on Earth ends up older than he is. That's quite a concept to get your head around. And I think so some of these films do an incredible job of communicating that. There's some things that you probably want to unlearn that you can't. And I know if I ask this question, everyone knows. How fast does the DeLorean have to go back in time? You don't need that information. But, there's a fun element to this, and I think if you can't enjoy the fun around adventurous science films, I think, yeah, relax.
All right, I think in the interest of time, we'll let Shane go, but he'll be around just because one more. One more, you say? Who said that so aggressively? Rachel, that's my sister. What is it?
I'm interested, do astronauts on the ISS age discernibly different from Earth? And
Do astronauts on the ISS age differently to if they were on Earth? Comparably to with they were on Earth.
Yeah, so in fact, there was a couple of gentlemen one of which was on the ISS. They were identical twins that were studied a few years back, and they knew that there would be a slight difference in age. It's very, very slight, but for me, being in an environment like the ISS, where you are, shall we say, far less protected from the radiations of the sun, I'm not sure I want to be the one that was a bit younger. So, overall, there is that effect. It is so small, though, relative to our lifespans that you don't notice it. You notice it with things like atomic clocks on the GPS system, but in terms of human beings, you don't notice it. But they did extensive tests on these two individuals. That probably aged them more than anything else. Yeah.
All right, give it up for Shane.